Good morning. This is Hope Reactor. Now, let's begin today's news.
The iPS heart muscle that grew stronger after just 3 hours of pressure. This heart muscle is working out outside the body. Inside a laboratory chamber, tissue made from human iPS cells beats on its own. But although it could contract, it still behaved more like fetal heart tissue than adult heart muscle. Its cells were poorly aligned, its energy system was immature, and its contractions were weaker. So how do you help artificial heart muscle grow up? A Japanese research team tried something surprisingly simple. They applied pressure for 1 hour a day over 3 days, just 3 hours in total. After this short training, the tissue became more organized, produced energy more efficiently, and showed features seen in adult cardiac muscle. Could it one day help people with heart failure? What we do not know can become hope. This is Hope Reactor. Why this matters? When heart muscle is badly damaged by a heart attack, it has only a limited ability to regenerate. The remaining muscle carries a heavier burden, which can lead to serious heart failure. For some patients, a heart transplant can be life-saving, but donor hearts are limited. This is why regenerative medicine has placed such high hopes on induced pluripotent stem cells, or iPS cells, which can be guided to become heart muscle cells. They may one day help repair damaged hearts and test new medicines, but producing beating cells is only the first step. The artificial heart muscle was still immature. Heart cells made from iPS cells can beat, but they are usually immature. Their structure is less organized. Their metabolism is different, and their ability to generate force is weaker. It is like an engine that starts but has not yet been fully tuned. If used for transplantation, immature tissue may not produce enough force. In drug testing, it may react differently from an adult human heart. Researchers have tested several ways to help the tissue mature. This team focused on something the heart experiences naturally: pressure. Every heartbeat exposes the heart to mechanical forces. What if artificial heart muscle also needs to feel pressure in order to mature? How the tissue was trained. The team combined iPS-derived heart muscle cells with vascular, endothelial cells, and supporting vascular cells. They placed them inside a three-dimensional structure containing proteins, such as collagen, creating tissue that could beat on its own. After growing it for 2 weeks, they placed it inside a special device and applied hydrostatic pressure. The pressure was delivered for 1 hour per day over 3 days. The total training time was only 3 hours. It was not meant to crush the tissue. The pressure acted evenly through the culture environment, allowing the cells to sense a change around them. And longer exposure was not necessarily better. The strongest effect came from short stimulation, followed by rest. Much like physical training, the tissue appeared to benefit from both the load and the recovery period. What changed? The first major change was alignment. In immature tissue, heart cells often point in many directions. In mature heart muscle, cells are arranged more consistently, allowing force to travel efficiently. After pressure training, the cells became more aligned and developed a more organized structure. A second change occurred inside the mitochondria, the structures that produce cellular energy. After pressure treatment, the tissue showed improved mitochondrial development and increased production of ATP, the molecule cells use as fuel. Calcium movement also improved. Calcium controls the timing and strength of each contraction, so better calcium handling means more coordinated beating. Most strikingly, the tissue began to show an adult-like response, in which faster beating was linked to stronger contractions. Its structure, metabolism, contractile behavior, and gene activity all moved closer to mature heart muscle. Why blood vessel cells were essential? The researchers then made another important discovery. When they created tissue without vascular endothelial cells and applied the same pressure, the maturation effect was greatly reduced. This suggests that heart muscle cells do not mature alone. The heart is a living community of muscle cells, blood vessel cells, and supporting tissue. To build realistic artificial organs, researchers may need to recreate those relationships. When the trained tissue was later placed in a flowing culture environment, it developed more internal vascular networks and moved even closer to adult-like function. Pressure trained the muscle, flow supported the vessels. Together, they made the tissue more lifelike. What happened after transplantation? The team then transplanted the trained tissue into rats with heart damage. 4 weeks later, the treated animals showed improved pumping function. Compared with animals that did not receive the tissue, human-derived heart muscle remained at the transplant site, and new cardiac tissue was observed. This does not mean the treatment is ready for people. The experiment was performed in rats, and major challenges remain. Researchers still need to produce larger tissues, create enough blood vessels, confirm long-term safety, and test the method in larger animals. Still, tissue trained outside the body survived after transplantation and contributed to improved heart function. The first practical use may be drug testing. Transplantation is only one possible use. More mature human heart tissue could also help researchers test new medicines. Some drugs appear safe in animals but cause unexpected heart problems in humans. Mature iPS-derived tissue could help researchers examine effectiveness and toxicity earlier. For that reason, drug development may benefit sooner than transplantation therapy. This is not a replacement for heart transplantation today, but researchers now have a clearer path forward. Conclusion. This study suggests that artificial heart muscle does not mature simply because it is kept alive for a long time. Cells learn from their environment. They respond to pressure and rest. They communicate with nearby blood vessel cells, and they change when exposed to conditions that resemble life inside the body. 1 hour a day for 3 days, only 3 hours of pressure training. That brief experience helped reorganize the tissue, strengthen its energy system, and improve the way it contracted. The future of regenerative medicine may not be only about making organs. It may also be about teaching them how to grow. Which field do you think will benefit first from this technology? Heart failure, treatment, or safer drug development? Tell us in the comments. For more stories about Japanese science, technology, and the ideas building a better future, subscribe to Hope Reactor. What we do not know can become hope.